This is Chapter 9, Problem 31. In this problem we have a person who has a mass of 90 kilograms in an elevator that's falling 36 meters, and we're going to calculate some things like the change in momentum and the force exerted on the person as they land if that impact lasts 5 milliseconds. So be careful here, that 5 milliseconds is just for the landing that will bring the person to rest after they've fallen 36 meters. Using those 36 meters, let's figure out the velocity of the person. So we're going to use our v squared is equal to v naught squared plus 2a delta x. We're working in the y direction here. We assume the person started out at rest, so v squared is equal to 0 plus 2 times 9.8 times 36 meters. And we get an initial velocity of 26.56 meters per second. We need to slow the person down from that initial velocity to 0, slow them down to rest. So the change in momentum is going to be equal to p final minus p initial. And that's going to be equal to 90 multiplied by 26.56, the mass of the person times their initial velocity. We don't have to worry about the final velocity because that's going to be 0. And again, we're not really worried about the minus sign here. So the change in the person's momentum is 2,390.4 kilogram meter per second. We assume that the person is going to experience a constant force in time. We know that impulse, change in momentum, is equal to force times the time interval. So that means that the force is going to be equal to the change in the person's momentum, 2390.4, divided by the time interval, 0.005 seconds, and we get a force of 4.78 e to the 5th newtons, which is a pretty massive force and shows you just what the human body is going to experience if you were to fall in an elevator shaft and land. You experience a tremendous amount of force. You probably saw on Mythbusters that at one point they asked, well, if you jump straight up in the elevator, won't that take away from some of the damage that's going to be done to your body? Be careful of the language here. What they're telling you is that you're jumping up at 7 meters per second relative to the elevator. So that means that the person's overall velocity is going to be 26.56, that's what somebody sees the elevator moving at, minus 7 meters per second. So this is going to give us the overall velocity of the person when they make impact with the ground, and we still need to slow them down. So now we're going to use the impulse equation. Delta p is equal to 90. We're still bringing them to rest, so the final velocity is going to be 0. And the initial velocity, since it's going down, it's minus the minus 26.56 plus 7. That accounts for the difference in the person's velocity relative to the elevator. This is what an outside observer would see. And we still get a delta p equal to 1760.4 kilogram meter per second. Using our force equation again, we're going to divide the impulse, the change in momentum, by the time interval, 1760.4 divided by 0.005. And we get a force equal to about 3.52 e to the 5th newtons. So you can see that the person is still going to experience a tremendous amount of force even though they jumped at the same time as impact with the ground. To recap, the hard part in this problem is realizing that the person's jump is relative to the elevator. So if we think of the elevator as stationary and the person jumping up at 7 meters per second, then that means that an outside observer watching the elevator fall at 26.56 meters per second has to subtract 7 meters per second from that to see the falling velocity of the person. The person is still falling. The person has not jettisoned themselves upward relative to a stationary observer. Use the impulse equation to figure out the force and see that it is tremendous because the time interval is so small.